This is the Chapter 43 lecture on population growth and species interaction. One of the first things we look at with population growth is what a population is, how we determine the size and the density of a population. A population is a group of interbreeding individuals. So as we've talked about before, a species has to be able to interbreed and have viable offspring. Well, a population is a species that lives in the same habitat at the same time. So if there are a bunch of water lilies out on a lake, that is a habitat, the lake, and all of the water lilies of that species on the lake make up a population. All of the humans in New York City make up a population. So population ecology studies the factors that affect how big populations get and how they change over time. We use tools like demography. Now think about demographic data, right? It's age, it's gender, it's a lot of times people will take into account religion or orientation of all kinds of different things, right? Race or things like that. Well, in population ecology, we look at birth rate, death rate, age, and size of population. The density, when we think about density, we're thinking about mass and volume, right? But in populations, it's the number of organisms per given unit of area. So for every square mile or whatever, it's how many people live or how many organisms are in that area, right? So when we quantify populations, we need to look at different ways to figure out who lives there. One way we do this is with a capture method. So we're actually catching the animals that live in that area. And we can use food to set out traps to catch them. And then with those methods, we can mark them with tags or just different other systems that will let them be identified as already marked. And we can let them go back out in the wild and recapture for our data. We also can do special sampling, like we can use video to record how things are coming in and out of an area. And then the sampling methods we use different ways to measure the amount of space we're using. So we can use a quadrant, which is like a 50 by 50 centimeter square, or we can use a line transect, so 100 meter of string. That's good for trees. So there's different ways to decide what areas we're looking at and how best to measure which organisms are there. So when we look at quantitative analysis, so we're looking at a population size, and the population size is equal to the number of marked individuals in the first catch times the number of marked individuals in the second catch, divided by the number of marked recaptures in the second catch. So if we caught 50 bass, tagged them and released them, a week later, we go out and catch another 50 bass. 5 of them were already tagged. How big is the population? Well, this one did 40 caught the second time instead of 50. So the way I had done it, it would have been 500. Right? 50 times 50 divided by 5 is 500. If you caught 40 the second week and 5 were tagged, then you have 50 times 40 divided by 5, which gives us 400. So that's how we look at the population size based on the capture and release method. Another thing we look at is the demographics, right? And one way we see things is through a life table. This gives us data on the individuals alive in certain age classes, and each organism is different. Not everything goes in years. Some things are in months. Some things are in years. Some things are in days. Think about a fruit fly only has a life cycle of a couple weeks, so we wouldn't measure months with them. Males typically are not included in a life table, and that is because they are included in offspring when we're looking at a total population, but as we're looking from one year to the next on fecundity or reproductive rate, that is a female thing, and fertility rate, that is a female thing. So we start with the starting population, which is marked as NX, where N is the number of individuals in the population and X is the age class. The number of deaths is DX. And then when we look at a comparison, we can say, like, what is the population in the 6th year? Or what is the population in the 6-year-old age group? Or things like that. So one of the things they also look at is how many people die during a certain time frame. And so in this one, it's looking at how many deaths in the 5th year happen after the 5th year. So you would take n to the 5, which would be number of population in age 5 class, in the 5th age class, minus the number of population in the 6th age class. And it gives you the D5 answer. So 273 minus 205 is 68. So we would see 68 deaths during that time. One of the things we can plot then is the survivorship of organisms and how that looks. So we plot the number of surviving individuals at each age. If it's a logistic scale and it's logarithmic, you will see that there's tons of population sizes that this can work for. And if you look up the side, you're going to see the number of survivors on that logarithmic scale. And across the bottom, the lifespan, young to old. So there are 3 different types of patterns that organisms can follow. The first is where the juveniles live a long time, and then most of the individuals die when they're old. And that's kind of the pattern that humans fall into. The second type is a uniform rate of decline. And that last slide we looked at had the life table of beavers. And this life table is showing a steady decline in the life or number of individuals in one population. So that uniform death rate just shows that decline in a linear fashion. And then the third type would be that the death rate for juveniles before reproductive age would be very, very high. And that as you get older, there's less of people in the population. And so it's slower loss for the survivors because the initial survivorship of infants is so small. Then we talk about age-specific fertility. Age-specific fertility is a rate at which female offspring are born to females who obviously have to be of reproductive age in order to have those offspring. So if we have 100 females in a population and they produce 75 female offspring, then we would multiply the number of females in the population times divide the number of female offspring by the females in the population and get that 0.75 as the age-specific rate of fertility. The age-specific rate of survivorship is going to be how many people are alive in each given age class at any given time. And that will lead to each age class's contribution to population growth. The reason we use these ideas is to calculate the reproductive rate of a population. And we use the reproductive rate of the population to determine whether a population is growing, declining, or maintaining equilibrium. So the net reproductive rate equals the sum of all age classes, rate of survivorship, times fertility rate. So we can look at this static life table for this set of sheep. So we're not counting births in this, only deaths, right? And that's why it starts at one end and it ends close to 0. X is representing the age class, and in this case, it's per year. N is the number alive. D is the number of deaths. L is the proportion of survivors. S1000 would be the amount alive if the population started at 1000 instead of 752. That part's a little confusing, but it's really just a reflection of the percentage. So if we look at how many newborns survive for the 0 age class, well, 100%. They were all born. Great. Then we look at age class 1 year. Well, there were only 623 survivors in this age class. That means we had 129 deaths. The proportion of surviving members is 623 divided by 752. And that gives us 0.828, which is where we get, when we multiply it times 1,000, 828 as the S1000 classification. In the second year, only 509 survive. So we add 114 deaths. The proportion becomes 0.677 of the original 752 population, which is why we continue to use that number instead of the number above. To calculate a future population size, we take our net reproductive rate, multiply it by the size of our population today, and that will give us the population size for the next generation. So when we think about those beavers, if we had 1,000 beavers and it was reproducing at a 10% higher than replacement rate, that's a positive growth. The population of the next generation, which is T plus 1, will be 1,000 times a 10% increase, so 1.1. That gives us 1,100. So this year we have 1,000. Next year we would have 1,200 beavers. The replacement rate is the number that keeps R0, or the population reproductive rate, the same. It will keep the population the exact same from year to year. It would always be 1,000. Then your net reproductive rate would be 0. Okay. Finite increases in population. So the finite increase from 1 year to the next is a ratio of the population size. Consider a population of 100 birds. These birds grow at a 5% increase. So it's positive, right? We're getting more birds from year to year. The question now is asking, what will the population be 5 years from now? So today it's 100. The next year it would be 100 times 1.05. But 5 years from now, we would do 100 times 1.05 raised to the 5th power. This would give us, in 5 years, 127.6, so about 128 birds. Remember, we can't have 0.6 birds. We only have 1 bird or 2 birds, not a half a bird. So population growth with regard to the finite example shows that this is increasing, and we can determine at what rate. We do know that T plus 1 equals N1 times the rate, R sub 0, right? Per capita growth rate is simply the number of births and deaths. So the change in number of population over the change in time will equal the number of births minus the number of deaths. So we can rewrite the equation. The per capita birth rate is the number of births per individual. the per capita death rate, the number of deaths per individual. So if a rabbit population has 1,000 rabbits and there are 100 births and 50 deaths every year, the population still increases by 50 a year because it has 100 born but 50 die. So we still increase by 50 rabbits. The way we calculate this then is the change in number divided by the change in time, and it equals 0.1 times 1,000 minus 0.05, because 100 is 0.1, right? Of 1,000 times to make 100 would be times 0.1. And then if we multiplied it times 0.05, we would get the 50. And that's how we're getting 100 minus 50 equals 50. So for exponential growth, the per capita rate can also be written as births minus deaths. The differential equation way is the number divided by the time. For the rabbits, we also could say 0.1 minus 0.05 equals times our 1,000 equals our 50. So if r is greater than 0, our population will be increasing. And in this case, it's increasing very rapidly. The characteristic curve that forms is a J-shaped curve. So you can see that the exponential growth is J-shaped. Exponential growth curves look like J's. Logistic growth curves look like S's. And the reason for this is because the logistic curve has limiting factors, things like habitat, food, other requirements for survival. And so the limiting factors limits the amount of growth that a population can have. Logistic growth has a carrying capacity, which we call K, and that is the upper boundary for a population. It is the maximum size that a population can get in order to sustain the same population size without growth or decreasing. The way we can find the carrying capacity is by looking at the change in population over time, and then it also will equal the rate times the population size, the growth rate times the population size, and then we take the carrying capacity minus the population number divided by the carrying capacity. So this model will fit most populations, but some it won't. Like, biology is totally an experimental science, and so as we manipulate things, we see whether or not it fits into the logistic growth curve or not. Some species have limiting resources, like food, like habitat, and other things do not. We can perform experiments and manipulate our data to determine what the carrying capacity would be. So when we have interactions between species, we look at different avenues of interaction. Sometimes we have competition. Competition typically results in a negative for both species because neither species is succeeding at getting 100% of what they need all the time. Another interaction we see is mutualism. This is positive for both species, and we see this a lot when certain species benefit from other species being around. The next is commensalism. So this is positive for only one species and negative for another. We also see predation, parasitism, and herbivory. Herbivory is negative for the plant, positive for the animal, the herbivore. When we look at mutualism, it's positive for both. So like positive for the plant, the bacteria in a gut and positive for the organism because the organism couldn't digest the plants it eats without that bacteria. Parasitism is negative for one species, but positive for the parasite. When we look at competitive characteristics in a population, we can see that in some cases, competition is okay, but in other cases, it's not. So Gauss found 3 paramecium species and grew them separately, and it followed a logistic curve. When he put 2 of the 3 species together, one species went extinct. When he put the original species that went extinct with the other species together, neither went extinct, but both populations went way down. So what happened? 2 species can coexist, but they cannot occupy the same niche. So the first 2, Caudatum and Aurelia, both occupied the same niche, so only one could survive. When we looked at Caudatum with Bracharia, neither went extinct, but they both had lower fitness because they were in the same area, but not exploiting the same niches. They may be using different food or different resources. This is known as coexistence. And the reason we can see coexistence is, as MacArthur points out, through resource partitioning. He watched 5 warbler species in New England and found that they occupied different heights or regions of a tree. And based on where they were in the tree, there were different insects living there. Based on those insect availability, the resources available were different for each species of bird. So 5 species of bird could live in the same tree as long as they didn't exploit the same niche. As long as they didn't eat the same food, they could all survive in the same space in the same time. And this is why similar species can coexist in a community. Competition is very common throughout communities and populations, and you can see field studies show this. When there's just a single pair of species, you will have more of the same resource because less is overlapped. But as more species are introduced that are trying to compete for the same organisms, you will see lower rates of survival and resources because they're using similar resources. The amount of competition will vary, dependent on the number of species competing for the resources. Plants show a very high degree of competition, as well as marine organisms. They tend to compete much more than terrestrial. Terrestrial organisms tend to move to a different habitat or a different niche. When you look at marine organisms, especially intertidal marine organisms, where as the tide goes out, now you have these organisms that live on the sandbars, that space is limited. And so competition is fierce there. Less resources, more organisms competing. So some of the things that we look at with predation, herbivory, and parasitism are: how lethal are they for the prey? Or the length of association between the consumer and the prey. When we see a high duration of interaction and a low lethality, those are parasites. It's good for the parasite, bad for the organism, but because it's not deadly, it can be sustained. But it takes a long time. Like if you have a tapeworm, you've got it for a really long time before you finally can get rid of it, or before you even know it's there. The next one would be something that has high rate or duration of interaction with high lethality. These are parasitoids. So you have this long interaction and then all of a sudden it's going to kill you. We look at herbivores. Low rate of interaction, low lethality. I mean, yes, some of the grass is getting eaten, but it's usually only some of the blade of the grass. The grass could still survive. Predators, however, are very lethal. They're going to kill you. But the interaction's not very long. And it's usually going to be in a group. And that's where, when we talked about in chapter 42, the herds and group living comes at a cost, but also at a benefit, more increased survival. So some things that organisms adapt in order to defend themselves from predators are defenses. Anti-predator defenses can be chemical or mechanical. And in this case, when we look at this bombardier beetle, it's going to be attacked by something. A predator comes and it sprays this really hot chemical spray on it and burns the predator. Well, that's great. Now it has a chance to run away. We also can see the blue poison dart frog, right? That blue poison dart frog, it gives off a special color that says, I am poisonous. Other things maybe taste bad. You lick it and it's like disgusting, like those caterpillars we looked at that are camouflaged, right? And then we see, okay, the effect is something terrible. We don't want to do this again. I just watched my friend eat a beautiful blue frog that died. Stay away from the blue frogs, right? In plants, they offer secondary metabolites, which are chemical. And these things are like nicotine, morphine, cocaine, caffeine. They typically make organisms not want to continue or do want to continue using, right? And with plants, if they want to make something continue using it, it will help it spread the seeds or pollinate. If they want something that's going to give an effect that they won't eat it, then maybe the effects of morphine, it numbs you and slows you down. And then all of a sudden, your predators can catch you. So maybe you would want to stay away from those things, right? The next anti-predator defense is camouflage. An example, this seahorse. Oh my goodness, or stick bugs. Stick bugs look just like sticks. This seahorse looks just like the coral it's being camouflaged in, right? And it blends into its environment. So it's less apt to be eaten by a predator. Another anti-predator defense is mimicry. Mimicry is a great one because you take a monarch that is absolutely noxious when it's eaten, and the viceroy butterfly will mimic its or is similar pattern to the monarch, and it's hoping that it looks so similar to the monarch that it no longer gets eaten. Now, it didn't intentionally make this choice, right? Over time, its traits were selected to follow the traits of the other butterfly, a monarch. Same thing when we look at these snakes. There's an incredibly poisonous snake, a scarlet king snake, and there's a coral snake. The coral snake is venomous, and it is mimicked by the scarlet king. It's hoping when predators see it that it looks enough like this coral snake that it scares them off, so they are not eaten. Maybe they'll go look for another snake. Another anti-predator defense is known as intimidation. And one example of this would be like the pufferfish. A fish swims by a pufferfish and it puffs all up and it looks all pointy and huge, and then hopefully its predators will run away. And finally, armor and weaponry. When we look at turtles, they have a huge defensive armor, right? Beetles, great exoskeleton, great armor. But also weapons like horns and antlers, these can be used in defense. So a lot of things can fight predators off with these adaptations. Predators can have major effects as well, and we see this with invasive species. When there's no natural predator to an invasive species, it will take over the habitat. So the Burmese python was introduced in Florida Everglades, and the normal things that eat the rodents and different species and organisms found in the Florida Everglades, we see the Burmese python now taking down. So these increases we have in these smaller species that are the prey of the raccoons and the possums, and now on top of that increase in those populations, we see the population of these being decreased because they're being eaten by the python. We see white-tailed deer being eaten, bobcats being taken down by all these pythons. There's no rabbits, no foxes, but they've got a plethora of all the things that those eat. So an example of this in the plant kingdom is the prickly pear cactus. Someone decided to bring in a prickly pear to Australia, and sure enough, it took over. It was an invasive species with no control, and it just took over the land. Thousands of acres of farmland are now covered in this species of cactus, and the sheep couldn't graze anymore. So they brought in this small moth, and the moth ate the cactuses, and because of that, it kept the population of cactus in check enough that it allowed the farming land to thrive, and the sheep could now graze. So we see biological species and interactions with nature are huge. Society impacts biology tremendously in positive and negative ways. But we can use society and the things that we know to help regulate biology when necessary. So some of the things that we talked about with relationship to organisms with one another were two things, were mutualism and commensalism. Mutualism would be a close association between two species in which they both benefit. One example would be pollination. It benefits the plant and the bee. The bee gets the nectar, the plant gets pollinated, win-win. Commensalism, only one member benefits, but the other member of the pair, the other organism, is not affected at all. So this would be seed dispersal, right? Mammals, their fur attracts these barbed seeds. It doesn't hurt the mammal at all. It's just their hair attracts it. And then it gets dropped somewhere else. So the mammal has no greater fitness, no negative fitness, but the seeds get dispersed further. So that's commensalism. And when we see types of factors affecting the species, we can see how it affects the density of the population. So density-dependent factors reduce a population. These are competition, predation, parasitism. These decrease the density or the number of individuals in a population. Density independent just keeps things totally sustained, right? These are physical things like weather, drought, floods, fires, and the mortality factor is not influenced or affected by the change in population size or the population density. The other density-dependent factor is a positive factor. And so this would say predators kill few prey when the prey in the population is low, more prey when it's higher. So if they're killing less prey, then it's increasing because the mortality is lower, right? So we can find positive slope or negative slope with regard to density-dependent factors, okay? Human populations. In 2001, the world's population was about 145 people being born a minute. And now this has been an exponential pattern. And it was very low up until we were able to begin agriculture and start domesticating animals. So between 1750 and 2012, the human population jumped from 800 million to 7 billion. Currently, the population is growing at 1.05% per year. And this is down. This downward trend has been for the last 5 years. We've been looking at this. The current average population is still increasing at an estimated 81 million people per year. People ask about the carrying capacity of the earth. Will we eventually not have enough resources to sustain our population? But the choices people make now in having births later in life and having less births per female, these things are affecting the rate at which the population grows. So it may not be as big of a problem as people have previously thought. That's all I have for you today. Have a great day.